Okay, what we have here is this loop where we've got a semicircle in the B field. The B field is coming out of the page, and the B field has this changing strength, 4t squared plus 2t plus 3. So it's getting bigger as time goes on. The B field, so therefore the flux is getting bigger as time goes on. So what we want to do is find the magnitude and direction of the induced EMF as a function of time. Okay. Well, we know the EMF is d phi dt, and so what with a negative sign, but we're going to use Lenz's law in that one. Okay, so EMF negative d phi dt, and what I'm going to do, d phi b, is I'm going to ignore that negative sign. I'm just going to do the magnitude. Well, the flux is equal to integral of b dot dA. B is out of the page, dA is out of the page, so the dot product goes away. And so if we really take this whole thing, the integral over that whole area, which is half of a circle, the B field is constant in there. So it's B integral of dA, which ends up just being B times 1/2 pi r squared. Okay, so here's my area, 1/2 pi r squared. Got the B field there, so there's the phi. Now, E is, and again, I'm going to ignore the negative sign. We'll use Lenz's law to get the correct direction. And so it's going to be d B, which is 4t squared plus 2t plus 3 times pi r squared over 2. That's a constant. That area doesn't change. dt. Now the derivative of this times this constant ends up being 8t plus 2 quantity times pi r squared over 2. That pi r squared over 2, when we use this r, ends up being 0.0628. 0.0628, if I've done my math correctly. So there's my my EMF, which is time dependent. If this were just changing as a function of time, it would be one thing, but it's actually, you've got a t squared in there, so the EMF is also changing as a function of time. In other words, the slope is getting steeper and steeper as a way of thinking of it. Okay, so there's my EMF as a function of time. What is the current? The current is just going to be EMF divided by R. Okay, and so that ends up being, we divide this by 2. I'm just going to divide that by 2. So it ends up being 8t plus 2, and you could absolutely multiply this out, but times 0.0314. And that is what I'm going to use as my I. Again, you could multiply this out, but I want you to see where it comes from. Now let's talk about Lenz's law. The delta B is out of the loop. Out of the page, right? So the B field is increasing out of the page because each of these things is getting stronger. Therefore, the B induced has to be into the page. And if the B induced is into the page, well, let's kind of figure out what would cause into the page. Well, if I do putting my fingers, let's assume an I in this direction, okay? Then that would wrap my fingers inside that coming out, so that can't be right. So it must be I going the other direction. I going in this direction, I going around like that. Okay, and so if I put my thumb in that direction, it actually puts the fingers into the page. So I is clockwise. Hey, we've got some other problems here. And so right now, I'm going to use this, and I'm going to say, let's find the EMF induced and the direction of the current. Well, B is 2 Tesla, and R is R0 times T. So this is getting bigger. And let's assume we've got more E field. In other words, it's not going outside the E field, which is not a trivial assumption there. So what we've got, we need to put down what the flux is, right? The B flux is integral of b dot dA. The b is constant. B integral of dA ends up being b times a, which ends up being b times pi r0t squared. And what I'm going to do is I'm going to actually evaluate that b times pi times r0 squared times t squared. The reason I'm doing that, I want to get all the t stuff alone. EMF is d phi dt, and so it's d b pi r0 squared t squared dt, and dt squared dt is 2t, so you end up with 2. I'll put the pi out front. B r0 squared, and that should be okay, and 2 Tesla. So this ends up being 4 pi r0 squared. Oh, I forgot my t, because remember this was 2t. I put the 2 out front, but there's my t. And there is my EMF. Direction of current. Okay, the flux is increasing out of the board. And we're getting more flux out of the board as that area gets bigger. So the flux induced, or I should say the B induced, will be into the board. And into the board, if I look at that left side, boom, the current needs to be clockwise. Okay, we pull the loop at a constant velocity. So we've got the square loop. We pull it at a constant velocity. Find the direction of the induced current and find EMF, I, and the force on the loop resisting the motion. And it will resist the motion. Why? Because think of energy, conservation of energy. If I put a little bit of force in there, if I do a little work here, right, it's going to change the energy somewhat. What would never happen is that this force ends up being, the force on the loop from the induced current ends up pushing it out faster. Think of that. If you pull on this and then it shoots out, that's a violation of conservation of energy. So what we want to do is, we know that force will be in this direction. Well, let's look at why. Okay, so if we have we pull the velocity, the loop in this direction, B out of the page decreases. So it's really delta B, B into the page decreases. So the delta B is out of the page. Okay, yes, the flux into the page is getting smaller, which is functionally the same as out of the page getting bigger. So the B induced ends up being into the page. What kind of current puts it into the page? I'll leave it as an exercise. I must be clockwise. Okay? So that's the first thing. Okay, so we've checked that off. Now, let's see. If I is clockwise, we can simply use the force is going to be integral of, equals IA cross IL cross B. Okay? IL cross B. So the current is going clockwise. It's going here, it's going here, it's going here. This will be out of that B field, so we don't need to worry about that. IL cross B, this experiences a force down. This experiences a force here. And please stop the video and use your right hand rule if you have any issues with this. These two will cancel, but look at that. That is resisting the motion. So we've demonstrated that it will in fact resist the motion. Okay? Excuse me. So we have FB equals IL cross B. The EMF equals negative d phi dt, but we're using Lenz's law to do that whole thing. Phi is going to be B times that area, B dot dA, integral of B dot dA, but it just ends up being BA because the B is in this direction, the A is in this direction out of the page, dt. Well, this is an interesting problem. I like these kinds of problems. So we have dB. Area is going to be this length, L. I'll make it capital L. And this is going to change as dx dt. I'm sorry, as x. This is going to be an x. I'm getting ahead of myself. This is going to be an x there, dt. So this just ends up being BL dx dt, which is just the velocity. So this ends up being BL dx dt, which is just the v, BLV. That's the EMF right there. So we've got that. The current is just going to be EMF divided by the resistance, which ends up being BLV over R. And the force, I'll come over here, force is IL cross B. Okay, and we've already said that's going to be in that direction. IL cross B gets you over there. So I is BLV over R. Okay, cross B and right angle. So we end up with, I'm hoping this works out. I'm missing an L there. Oh, I forgot my L. There's my L there. So there's my I times L times B, and you end up with B squared L squared V over R. Ends up being that force resisting the motion. So once again, we do, just to find the direction, I like to do that first. We found the direction of that current, but really we could do the EMF first. EMF d phi dt. The area is changing now. B is constant. The area is changing as dx dt times L. There we go, BLV. Then we use that to find the current. Then we use IL cross B to find the force.
Dinner's ready.
Okay. Here's another problem that's kind of a classic problem in B fields. Okay, this is falling down with a constant velocity. Constant velocity, of course, means balanced forces. Falling down means we are actually talking about mg, and this means that the magnetic force on there has to be up. So this is going to be equal to IL cross B. Okay, so we need to figure out what the I is and what the velocity is. And so the first thing we're going to look at on this one is IL cross B is mg. IL cross B has to equal mg because FB equals force of gravity. Okay. And the, excuse me, so the EMF is going to be d phi dt. Again, negative sign, but I'm ignoring that. I'm just going to talk about the magnitude. Okay. And phi is going to be B times A dt. And remember, BA, this we have a length here, and we have a, I'll just call it a height here. So B is constant, dA dt. And dA dt is going to be B L dH dt, which is just the velocity. Okay, BLV. See that a lot, by the way. You see that a lot on these things where the area is changing because of overlap or because of, in this case, a crossbar that has conductivity with those sides there. So we've got the EMF there. And so the current ends up being the EMF over R equals BLV over R. And so the force ends up being BLV over R, current, times L, cross 90 degrees, we should be okay, times B there, equals mg. So the velocity ends up being mgr over b squared L squared.